Dear students, Assalamu alaikum. We have discussed complex valued functions and their continuity and differentiability. We know that a complex valued function is called analytic at a point z0 if it is differentiable at z0 and in some neighborhood of z0. For this purpose, we often utilize CR equations in Cartesian form, which is an equivalent criteria for differentiability. Now, if a complex valued function is in polar form, then we need an equivalent form for CR equations in polar form. Let us derive CR equations in polar form. We know that in polar form, x equal to r cos theta, y equals to r sin theta, and Cauchy Riemann equations in Cartesian form are ux equal to vy, vy equals to minus vx. Let us write ux, uy, vx and vy in terms of in its equivalent form of polar coordinates as ur, u theta, vr, v theta. For this purpose, we are going to use chain rule for multivariable functions. Suppose that uxy is differentiable function of x and y, where x and y are differentiable functions of r and theta. Then we can write partial u or partial r as partial u by partial x by partial r plus partial u by partial y by partial r, and this is elaborated as in tree diagram. And you can see in number 1 we have to write partial u by partial r. U depends on x and x depends on r. Therefore, partial u by partial x into partial x by partial r plus u depends on y and y depends on r. Partial u by partial y into partial y by partial r. Similarly, we can write partial u by partial theta equals to partial u by partial x by partial theta plus partial u by partial y by partial theta. Given u and v be the two components of complex valued function f of x plus iota y equals to u plus iota v, then partial u by partial r is equal to partial u by partial x by partial r plus partial u by partial y by partial r. As we know that x equal to r cos theta, y equals to r sin theta, so partial derivative of x with respect to r is equal to cos theta and partial derivative of y with respect to r is sin theta. Therefore, we can write partial u partial r as ur and partial u partial x as ux. Partial x by partial r is equals to cos theta plus partial u partial y as uy, partial y by partial r as sin theta. And equivalently, you can write u theta equals to minus ux r sin theta plus uy r cos theta. Also, in terms of v, you can write vr equals to vx cos theta plus vy sin theta and v theta equals to minus vx r sin theta plus vy r cos theta. We can write u theta equals to minus r into ux sin theta minus uy cos theta. Actually, in the expression of u theta, r is common from these two terms. So taking r common from these two terms with negative sign, we can write minus r ux sin theta minus uy cos theta. And we also know that ux is equal to vy and uy is equal to minus vx by CR equations. Therefore, this expression is equivalent to VR, and we can write u theta is equal to minus r VR. Similarly, the second equation will be RUR is equal to V theta. We can write it as in another form UR equals to 1 over r V theta and VR is equal to minus 1 over r U theta. In Cartesian form, f of z is equals to u of xy plus iota v of xy, and we can write the derivative f prime z u of x plus iota v of x or f prime z equals to v of y minus iota u of y. In polar form, we know that x equal to r cos theta, y equals to r sin theta. And in polar form, function is u of r theta plus iota v of r theta. Now we show that in polar form, f prime z can be written as u of r plus iota v of r into e power minus iota theta, or f prime z is equals to minus iota over r u of theta plus iota v theta into e power minus iota theta. For this, we can write partial u by partial x or u of x as partial u by partial r over partial x plus partial u by partial theta by partial x, as u of x is equals to ur cos theta minus u theta sin theta r. Partial r by partial x and partial theta by partial x are explained in this slide. We know that r square is equal to x square plus y square and theta equals to tan inverse of y over x. By differentiating r with respect to x, we will get partial r by partial x equal to x over r, and in polar coordinates x is equals to r cos theta, and after simplification we will get partial r by partial x equals to cos theta. And now differentiate theta with respect to x, we will get 1 over 1 plus y square over x square into minus y over x, that is the derivative of inverse tan function. After simplification, you can write it as x square over x square plus y square into minus y over x square, that is equals to minus y over x square plus y square, and you know that y is r sin theta and x square plus y square will be r square. Therefore, it is minus r sin theta divided by r square, and after simplification, you will get partial theta partial x equals to minus sin theta over r, and v of x is equals to partial v partial r by partial x plus partial v by partial theta by partial x, or we can write it as vx is equals to partial v partial r as vr, value of partial r partial x is cos theta, v of theta partial x is equals to minus sin theta over r. Using equation number 2 and 3 in first part of equation number 1, we get f prime z is equals to u of r cos theta minus u of theta sin theta over r plus iota Vr cos theta minus V theta sin theta over R, using CR equations in polar form. So f prime z will be equals to u of r cos theta plus V of r sin theta plus iota V of r cos theta minus u of r sin theta. Now we can write cos theta taking as common from first step and third term u of r plus iota V of r into cos theta, and sin theta common from second and fourth term, we will get V of r minus iota u of r into sin theta. We can write V of r minus iota u of r as u of r plus iota V of r by taking minus iota as common. So taking common u of r plus iota V of r from first quantity, also from second quantity, we will get u of r plus iota V of r into cos theta minus iota sin theta. And cos theta minus iota sin theta, after applying the Euler's formula, we can write it as e power minus iota theta. So finally, f prime z is equal to u of r plus iota V of r into e power minus iota theta. That is the expression of derivative of f in polar coordinates. Again, using CR equations in 4 as u of r equals to 1 over r v theta and v of r as minus 1 over r u theta, we obtain f prime z is equals to u of r plus iota v of r into e power minus iota theta, u of r equals to 1 over r v theta, and v of r equals to minus 1 over r u theta. By taking minus iota over r common, finally we will get u of theta plus iota v of theta, and derivative of f prime z is equals to minus iota over r into u theta plus iota v theta into e power minus iota theta. That is as required. Now we prove another very important result, that is called Laplace equation in polar form. We know that Cauchy Riemann equations in polar form are ur equal to 1 over r v theta, vr equals to minus 1 over r u theta. Now differentiate equation 1 with respect to r and 2 with respect to theta. We will get urr equals to minus 1 over r square v theta plus 1 over r vr theta. That is applying the product rule of differentiation. And v of theta r equals to minus 1 over r u theta theta. Multiply equation 4 by 1 over r and then adding to equation number 3. We get urr is equal to minus 1 over r square v theta, and in place of vr theta we replace minus 1 over r u theta theta, which will result in minus 1 over r square u theta theta. Therefore urr equals to minus 1 over r v theta minus 1 over r square u theta theta. And finally we get urr plus 1 over r square ur plus 1 over r square u theta theta is equals to 0, which is Laplace equation in polar form. We can also write equation 5 in terms of v. Note number 1. If ur theta satisfies Laplace equation 5 and vr theta satisfies Laplace equation 6, then ur theta and vr theta are called harmonic functions. 2. If ur theta is harmonic, then we can find its corresponding conjugate function vr theta using CR equations in polar form, and then can find f of z equal to u of r theta plus iota v of r theta as original function. 3. For finding conjugate function v of r theta, use same procedure described in lecture number 13.